Okay, so I think we are also live on YouTube. So thanks to everyone for joining today. I have Arjun here with me, and Aryan is here, Shubhodip is here, Auditro, Sarvam, and I think Jatin has also joined. So a ton of people have joined to discuss some exciting problems. Let me just start with Auditro. Auditro, you have writing access to the Jamboard, right?
Yeah.
Okay. So why don't you, which problem would you like to start working on?
First, I start with the problem number 6 because it's actually a very beautiful. It's actually a combination of geometry and algebra. It's one of my favorite
Okay,
problem. You
okay,
can
okay.
say
That's great. So
that.
let's start with problem number six. So what I'm going to do is I will put problem number six on the Jamboard so that people can, see it. And just a second. Let's see. I will put the problem number six on the Jamboard. Yeah. Sorry, it's taking a little bit time, but I will just go ahead and put it here. Yep, it's. I thought we can drag and drop photos, but maybe not. Here is the problem number six. This is the. I'll change the
Yeah,
background a little bit. So Arithro, can you see this
yeah, yeah, sure.
document?
I think I should change the background to black. It is much better looking at.
Oh, really? Okay, that's great.
Yeah.
Take it.
All right. So, see, first of all, let's try to understand the motivation of the problem
Uh-huh.
because I personally think the motivation is very important rather than solutions. So, let's understand the motivation. So, what is given? Here it is given that x square plus y square equal to 49 and y square plus yz plus z square equal to 36 and x square plus this thing equal to 25. So the first question that all of you first think that why they asking for this type of weird looking value? Why not? Oops, what happened?
Oh, something. Oh, did the.
Something went
Just a
wrong. Actually,
second.
I
Let me
think.
try this. Now is that better?
I think this
Okay.
screen sharing stopped
Okay, I'll
somehow.
just share the screen one more time. Just a second. Yeah, now I think people can see it. Yep. Yeah, I think it's back.
Okay.
Yeah.
Yeah. The first thing is that why they are asking for this type of thing and why not the exact value of x, y, z or something like that? What is the reason behind that? That is the first question appear to my mind, or all of you can think like that. Or where we have seen these type of things means first of all think that can you recall any place where you have seen this type of things y square plus yz plus z square equal to 36 and x square plus yeah means if you think properly you have seen this probably in two places. One is when you open the bracket in the square perfect square you have probably have seen there, but another thing you can actually thought of is as a cosine rule, right? It's quite weird looking, but still you can feel like the cosine rule means it is quite simple looking, but it is seem like the Pythagoras theorem. But if you think Pythagoras theorem, but in much more detail, you can realize the Pythagoras theorem is nothing but just a special case of cosine rule. So here the same thing actually applicable, that we first try to understand what is the cosine rule and then try to proceed it. So I think all of you know that if we have a triangle ABC here and it is B, it is C, then the standard thing is just C square equal to A square plus B square minus 2AB cos C. It is similarly the rest of the thing actually follows cyclically for B and C. So see that it is almost same. Even this is if you think for this side 49 is 7 square, 36 is 6 square, and 25 is 5 square. Okay. So one thing means this c square type thing is already there. We have nothing to worry about too much. It is already there. And let's try to understand this thing. If you, I am not very much worry about this because all of you can understand that there is some play of right angle triangle and everything. I'm not interested in this. Let's talk about this one. Okay, so if we compare this thing, you can feel that it is something like this: 6 squared equal to a squared, means you can think as y squared plus b squared. What is b squared? B squared is z squared, and then minus 2ab. Okay, so here is 2. 2, first write down 2, then ab. So let's take ab. Instead of ab, I'm taking yz, and cos c. But cos c is here is plus 1. You can see this is plus 1. So how can I bring plus 1? If I take minus half here, then the plus 1 thing is balanced. Similarly, if you look for this, it is nothing but 5 square equal to x square plus z square minus 2yz. Again, this can be thought as minus 3 root 3 by 2. See, that root 3 plus root 3 actually properly comes. Now, if you are more careful about some cosine value, then if I'm not very wrong, then this is cos 120 degree. And if you careful about this, this is nothing but cos 150 degree. Okay. Okay, and I'm just writing down the second part, means this seventh one like this also, so you can actually feel the beauty of this entire thing, that 2yz, and also you can relate that how Pythagoras theorem actually appeared from cosine rule. That may be helpful for some other problem beyond this problem actually, I'm thinking. So it is 0, we can think is 0, but 0 is nothing but cos 90 degree. Okay, now the configuration is very beautiful. Observe that 120 degree, 150 degree, and 90 degree, when they sum up, they give 360 degree. Okay, so now let's see the beautiful configuration that is actually key configuration for this figure. And I suggest you, means though I am giving this particular problem using completely geometrically shorter one, but if you properly manipulate this, you can also solve it completely algebraically. Means instead in the exam hall, if you are very uncomfortable with these stuffs, I'm suggesting you please think how can algebraic manipulation can resolve this problem. And it is possible. Okay, whatever. Get back to the thing. So suppose this is my figure. Think about a point P. Okay, I should change the color. It is not a good.
Yeah, it is
Think
amazing.
about the point P like this, and then you take the line segment like this. Here is the point. Okay, right. Suppose that this is 90 degree, this is 120 degree, and this is 150 degree, right? It is 150 degree. So now you think AP, this particular length, so see 90 degree is the angle between X and Y. So you can think as this as X and this as Y. So observe that X square plus Y square, how beautiful it come in what is this, 7. Okay, 7, and X, and this is Z. So again you observe that X square plus Y square minus 2YZ, it is actually 6, I think. No, or not 5. And if you see that this is actually 6. Okay, this is actually 6.
Right.
And what is the much important thing, means it is all everything all right, but I'm saying about much bigger one. Suppose you can actually solve this type of equation, a square, b square, c square, anything can be written in the forms of square. But one thing you have to care about, what? That these three things really make a triangle. So you have to very careful about the triangular inequality. Okay, means whenever you see, if you blindly start to apply, then this method may not work, because here is a special thing that it works because they prefer that works, but sometimes they give some numbers that actually doesn't follow the triangular inequality.
So
So that's why
basically
it
they
is.
have set it up in this way, right? Set
Yes,
up the
yes,
numbers in
exactly.
this way. Yeah.
And so that's why I suggest all of you that if you are looking in this solution, then also try to solve it algebraically, completely algebraically. That also give you some other horizon to uh, means approach. That's the thing.
Right.
Okay. Now the next question. This goes the first one, that why these things are this type of weird looking. Now the next one, why they are directly giving this value, not actually the value of uh, this xyz. Then why they are not actually trying to find it out? Okay, so there is also a reason that what I'm going to do here, I am count the same object into different way. That is one of the most powerful tool in the mathematics, you can say, that we often count the same object into different way, then we combine them and make some beautiful conclusion. Here is the same thing. So here I am going to use the thing. um, that's the idea. So see that if we have the triangle, so next thing, that why this is a product like that. You have seen this type of product when you try to find out the area. So let's try to find out the area into different way. So what are the two different ways? One way is this: I just find out these three area and simply sum it up, right? Sum of these three area to find out this thing. And the second is this, that you can directly use the Heron's formula and everything to find out this area. So first, let's do the easy case, that is using just Heron's formula. Sorry for the bad handwriting. Um, the semi-perimeter S, if I'm not very wrong, just let me check 1 minute. The semi-perimeter S is 9. Okay, and if we use this classic formula, that root over S into S minus A into S minus B into S minus C, that's we often use, you find out the area is something like root over of 216, that is I think 6 root 6. But okay, whatever, the not calculation part is not very serious, just understand the concept, because calculation is just uh, not too much important in this. At least to me, calculation is not important. Okay, and the second way is that I preferable to find out these three area. So what can I do to do this thing? First of all, see the area of APB. What is the area of APB? So okay, I will just take the square bracket to represent the area. So area of APB is basically equal to what? See, it is 90 degrees. So simply half of x into y. So half xy, and then b. Okay, so here a quick recall, means I'm just making a quick recap for you. Is a quick recap, or if you know, that's a very good thing. That if we have a triangle ABC and the intermediate angle is theta, and this side is A, this side is B. I'm not taking the usual notation, anything. I'm just taking the area is basically half AB sine theta. So I'm going to use this thing. So we know that this intermediate angle is 120 degree. So it is nothing but the area of BPC. The area of BPC is equal to half of 20 degree. Now sine 120 degree, if I'm not very wrong, then it is half. So it became 1 by 4 yz. And
So root 3 by 2.
oh, sine 120 degree means 90 plus 30 cos, yes, sorry, yeah, root 3 by 2 yz. Thanks. And the last one is APC. So APC equal to half xz sine 150 degree. So this is, I think, 150 degree means cos 60 degree. Cos 60 degree is minus of cos 60 degree, half. So it will be 1/4 xz. Right. Now we sum up. What you get, half xy plus √3/2 yz plus 1/4 xz. This is one way to calculate. Already we find out here, that is 6 √6. So it is equal to 6
You
√6.
said root 3 by 4.
Huh?
Before YZ is root 3 by 4 coefficient.
Or √3/4. Yeah. Now clear the coefficient multiplying with 4. So here should be also by 4. Multiply the coefficient, means clear the coefficient. So it is 2xy plus √3yz plus xz equal to 24 √6. It is your p, it is your q, everything is here. Now you can easily find out the value of p plus q. Okay, some point that I certainly say after the solution, it is the final thing, and you can check that it is exactly the same format that is given. Some important tool that, or some important point that you should notice before, means I point out before ending the solution, is this, that first of all, the thing is that we have to follow the triangular inequality. Okay, means the number that is given should follow triangular inequality.
Right, the three
And
sides.
another thing that is also very important, that these three angles really sum up to 360 degrees. Otherwise, the entire method fail, right? So it is a very important point that sum of triangle equal to 360 degree. Okay, and here the end of this beautiful problem.
Okay, thank you, Arithro. That was awesome. I think we will now move on to another solution, which is, I would let me just describe the fourth one, fifth one. I'm sorry, fifth one. Problem number 5. So I will have to put the problem first here. Just a second. I think I have it here. Yeah, I think I have that. Yes. So here is the problem number 5. Let me make it larger. And okay. So all of you can see this problem, right? The problem number 5. Yeah. Okay. So let's first draw the picture if you can. So let me use a color here. So we have a parallelogram ABCD. So it's like this, a parallelogram A, B, C, D. I hope this is visible. And this solution was suggested to me by one of our faculty members, Shaddam. So thanks to him. It's pretty nice actually. So there are bisectors of 4 angles of the parallelogram, like this, and they form a little quadrilateral. If you can see, there is a little quadrilateral inside the parallelogram, and the name of that quadrilateral is XYZW. Okay. Now, what is the given data? Given data is this. Given data is that AB is 2 times BC. It's the first thing. AB is 2 times BC. And it's also given that the area of XYZW is 10. So these are the two things that is given to me. Area of XYZW is 10, and there are angle bisectors, the angle bisectors of the parallelogram that are making this particular quadrilateral in between. And the area of that quadrilateral is 10. And it's also given that AB is twice BC. This is all that is given. This is the given data. So how do we go about it? So first, one of the first observation is that now I'll give a, this is something I'm also thinking about it. Maybe we can do this purely by geometry, but there is a very nice solution using trigonometry. If you have used trigonometry, you will be able to do this very quickly. So let's first set it up properly. This particular angle, suppose it's theta. If this particular angle is theta, the first observation is this, that this is a rectangle. Let me write that. Maybe I'll write it using a different color. So claim 1 is that XYZW is a rectangle. So why is that? Well, you can easily calculate this. See, one way to see this is like this. This angle is d by 2 and this angle is d by 2, because both of them are, that is an angle bisector of angle D. This is a by 2 and this is a by 2. So the angle right here is, the angle here is 180 degree minus a by 2 minus d by 2. But notice that a by 2 and d by 2, they add up to 90 degree, because a plus d will add up to 180 degree. Can anyone tell me why a plus d, angle a plus d will add up to 180 degree? Why is it so that angle a plus angle d adds up to 180 degree? Because AB and DC are parallel, so the angles adds up to 180 degree. Absolutely. So if you divide that by 2, you will get 90 degree. So 180 degree minus a by 2 plus d by 2 will be just 90 degrees. So this angle right here is 90 degrees. Similarly, you can show that all of these angles, all of these corner angles of this quadrilateral in between, that is 90 degree, making it a rectangle. So XYZW is a rectangle, which is, of course, something that's a first observation. Okay, now let's do one thing. So if this is 90 degree, if this angle is 90 degree, then we can change this a little bit. This is d by 2. Let's make it theta actually. Let's make this angle theta, just to make the calculation clearer. So this is 90 minus theta. This angle is 90 degree minus theta. Okay, I'll just clean up some space here. Okay, so, and this angle is also angle theta. All right, so that's great. That's 90 degree minus theta. Okay, so notice that this angle is equal to this one because it's a parallelogram, right? Angle A and angle C will be equal. Since this little angle is 90 minus theta, this angle will also be 90 minus theta. So this is 90 minus theta. I will remind you that these are angle bisectors. This is the angle bisector of angles A. So if this is 90 minus theta, this is also 90 minus theta. So this is half of angle A. 90 minus theta is basically half of angle A. So half of angle C will be equal to half of angle A, because A and C are equal angles. It's a parallelogram. So this is a 90 degree, 90 minus theta. So this is also 90 minus theta. And this is theta again. So we are marking all the angles and we know them because we are working inside the parallelogram. Okay. So now we are almost ready. Just to make sure that we understand this side condition. So assume that AD is T, the length of AD is suppose T, then length of DC will be 2 times T. That's another given condition, that AD is half of DC, that is one of the sides is half of the other one. Okay, that's great. So we are almost ready, uh, in the sense that if you now apply simple trigonometry, you will be done very quickly. See, dx, this is t cosine theta. In a right angle triangle, whenever you have a right angle triangle, this is angle theta and this is the hypotenuse, you should think about the base and the height as projections of the hypotenuse. Think about it. If you have seen this for the first time, think about it like this, that whenever you see a right triangle, the base and the perpendicular, you should not think of them as base and perpendicular. You should think of them as the projection of the hypotenuse, the horizontal projection of the hypotenuse, and the vertical projection of the hypotenuse. The horizontal projection of the hypotenuse is t cosine theta. This is t cosine theta. And the vertical projection of the hypotenuse is t sine theta. T cosine theta and t sine theta. This is, if you are seeing this for the first time, it might be a little bit confusing. If you are seeing this, if you have seen this before, then it's simple. Okay, now if you look at this, now look at this particular triangle. That's the trick. You look at triangle DYC. DYC. This is also a right triangle. Triangle DYC is a right triangle. This is 2t. This is angle theta. So this much is 2t cosine theta. This dy, let me write it here. Dy is 2t cosine theta and dx is t cosine theta. That's what we found earlier. So if you take the difference, you get the value of xy. So xy is simply t cosine theta. So let me write that. Xy is t cosine theta. Okay, now you can also find out the value of this much, xw. Exactly in the same way, you can find out the value of xw. Okay, let's see how we can do that. So if you look at this particular side, cy is 2t sine theta. 2t sine theta. And if you look into this particular triangle, you will be able to see that CZ is t sine theta. CZ is t sine theta. CZ is t sine theta. So what you have here is YZ turns out to be t sine theta. So that means this particular rectangle XYZW, its area is t square sine theta cos theta, t square sine theta cos theta, which is simply 10, because that's given. The area of the inside rectangle, the inside quadrilateral, is given to be 10. So you know t square sine theta cos theta is 10. You want to find out the area of this parallelogram. So how do you do that? Well, you notice that this side is t, this side is 2t, and this angle is 2 theta. So area of the parallelogram, maybe I can write it here, is AD times DC, sine of the included angle, sine of the angle in between, which is 2 theta. AD is t, CD is 2t. So t times 2t sine 2 theta, this is the area of the parallelogram, which is 2t square 2 sine theta cos theta, or which is 4 t square sine theta cos theta. So you already know that t square sine theta cos theta is 10. So you can replace it by 10. So it's 4 times 10, which is 40. That's the final answer. So 40 is the final answer of this. And I should mention again that this was suggested by Shaddam, one of our faculty members. So thanks to him. Now I will go to, let me go to Arjun a little bit. Arjun, are you there? Hello, Arjun.
Yes, sir.
Okay. Could you tell me what problem you would like to discuss? Which one?
Sir, maybe problem 12.
Problem number 12. So let me, so you have a way of writing in the Jamboard?
Yes, sir, I can write.
You can write in the Jamboard, right? Okay. Let me just upload the
Uh,
question first so that you can see it. Students can see it, sorry. So here is the question number 12. And I am in the board 4, fourth board. Yeah. Okay. Yeah.
yeah, so we more generally solve the problem when 12 is replaced by n and 7 is replaced by some k plus 1.
Okay. So can you write it in a more darker ink so that students can see it more clearly?
Okay, maybe reading.
Red
We will
and
show
black is
that the
fine.
answer is uh, what, sir?
Yeah, go ahead.
Yeah, we will show that the answer is nk plus 1. So for this special case, answer is 73. But we will solve this problem only.
Okay, just a
So
second.
first we show that.
Let me explain the problem to the students a little bit. The problem says that the 12 cross 12 board, a 12 cross 12 board, like a chess board, it's like a chessboard. So it's divided into 144 units squares, like drawing parallels and sides and so on. So in the shorter version, if I draw it in a shorter version, that's allowed. So maybe I can do a 4 cross 4 board. So 1 2 3 4, 1 2 3, and that's what 16 squares. It's like just like a chessboard, and you have two rooks placed on 2 unit squares are said to be non-attacking if they are not in the same column or in the same row. So if you have two rooks like this, of course they will be attacking, right? But because they can just, rooks move either parallelly or horizontally, like horizontally or vertically. So if they are not in the same row or the same column, then the rooks are non-attacking. For example, these two rooks are non-attacking. Find the least number n such that n rooks are placed on the unique squares. One rook plus square. We can always find 7 rooks such that no two are attacking each other. So you want to put 7 rooks on the board such that no two of those 7 rooks are attacking each other. And Arjun is going to tell us a generalized version of this problem. So just before Arjun begins, I have to tell you this, that this sort of this one of this type of chessboard problems with non-attacking rooks or queens or whatever, that one such problem was recently solved by a Harvard mathematician. You can check it out, the queen problem of mathematics, that has been solved very recently. So I think Arjun and others can also check it out. But this is very nice. Arjun, go ahead and tell us what you have in mind.
Yeah. So actually, in general, if we look at this problem in terms of bipartite graphs, then it has like a known statement that if we that it's saying that what is the minimum number of edges there need to be so that there is always at least a k plus 1 length matching. But we can ignore that bipartite graph formulation also because this is simpler.
Okay.
So okay. Uh, First, we show that nk if first we place nk rooks such that no k plus 1 rooks attack each other.
Okay.
So like we pick any k rows and and fill them fully.
Okay.
Put a rook in every each of the unit squares.
Okay.
In that case, we have placed nk rooks in total, but it is clear that if we pick any k plus 1 rooks, then by PHP, some two will be in the same column.
Okay.
So this means that some two of them would attack each other.
Right.
So we have shown that we have found a construction for nk. So if we could just show that given any nk plus 1 rooks placed, we can find some k plus 1 which do not attack each other.
Okay. So can you sort of give an example of this argument in like a smaller version? Let's say 5 cross 5
Okay.
board with, so n equals to 5 and k equals to 3, maybe something like that.
Okay, I'll give it on the next page. Uh,
Okay, that's fine.
uh,
So that all of us can
uh,
follow the argument. So this is a, so just to make sure everyone understands this, this many of the problems that came up in IOQM this year are actually classical problems that are already known, right? I mean, many of you have noticed that some problems came from um, like directly from test of mathematics or past Olympiads and stuff like that. So
eh, yes, sir. In fact, this result is also a bit known, like it has occurred before in some
yeah, yeah.
handouts.
So again, can you put the rooks in a darker shade, maybe?
Okay, I'll put them in black. Okay, so like basically for n equal to 5 and k equal to 3,
Okay,
we want to find the minimum number of rooks we have to place such that we can always guarantee some 4 rooks do not attack each other.
right.
We are claiming that the answer is 5 times 3 plus 1 equal to 16. 5 times 3 plus 1 equal to 16. We are claiming this is the answer.
So you are claiming that if we put 16 rooks on this board, 16 rooks, 1 6,
Yeah.
what would happen?
Yeah. Then we could always find some 4 rooks which do not attack each other.
So out of those 16 rooks, there will be 4 rooks which do not attack each other. Okay.
Yeah. So so for
Why is
that we
that?
first show that we can put 15 rooks. Otherwise, like someone could give an argument for 15 rooks and our
So are you
answer would
saying
be wrong.
something? I can't hear you.
So
Yeah.
the construction to put 15 rooks is as follows, like we pick any 3 columns and fill them completely.
Okay.
In that case, it is easy to see if we pick any 4 rooks, then some 4 of them will be in the same column. Like some 2 of them will be in the same column by pigeonhole principle.
Okay. Yes.
So this means some 2 of them will attack each other, which shows our construction part that there is no argument for 15 rooks.
Okay.
Now the next thing we have to show is that we can that if we put only like if we are given 16 rooks, then we can always find 4 such rooks.
Okay.
So we assume contrary that we cannot find 4 such rooks.
Okay.
Suppose we can find 3 such rooks. If we can't even find 3 such rooks, then we just keep randomly placing more rooks until we can find 3 such rooks.
Okay.
Like we assume we can find 3 such rooks. Suppose we were only able to find 2 such rooks, then we keep adding more rooks and until we could find 3 such rooks.
Okay.
Now suppose these black three rooks are the three such rooks like which clearly do not attack each other.
All right.
Now in this case, if we look at these two squares,
Mm-hmm.
then these two cannot, then both of these cannot contain a rook. Otherwise, we could replace this black square with these two, and that would create four rooks that attack each other. Four rooks that do not attack each other, which would be a contradiction.
Okay.
Similarly, if we look at these two squares, both of these cannot have rooks. Otherwise, again, we could find four rooks which do not attack each other. Like we could do this pairing. This square gets paired with this square paired with get this. Now, finally, we have this inner 3 cross 3 square. One last argument is that, of course, these four squares cannot have a rook. Otherwise, we of course get four rooks which attack each other by picking any one of them.
Mm-hmm.
Uh, so now finally only this much part is relevant for us, and now in the best possible case this black square will contain 9 rooks, plus we have shown that among these 12 squares we can basically pair the unit squares such that in each pair at most in each pair at most one unit square can have a rook. Both cannot have rooks, otherwise we get four rooks which do not attack each other.
Mm-hmm.
So this basically shows that number of rooks is at most 9 plus x equal to 15. Here 6 is equal to like 12 by 2 to be more precise, but which is a contradiction as we assumed that there are at least 16 rooks.
Okay.
This this directly generalizes to the general case. This numbers 5, 3, 4 are nothing special. They were just chosen to make our work easier, but this directly generalizes.
Okay. Okay. Maybe if we write down this particular solution a little bit more carefully, then it would be a bit more clearer. Okay, fine. Thank you, Arjun, for the comments. Let me go on to, so those of you who are watching this, I would say we are uploading the solutions and discussions in the Chinta.com. You can go there and see there is a top link that is active now. You can try to use that after the session is done. But now let me go to Aryan Prakash a little bit. Hello, Aryan. Can you hear me? Are you there?
Yes, yes, sir.
Okay. Would you like to comment on any of the problems that have come?
Sir, can I do problem 11? All right,
Problem
nice.
number 11. Okay. So yeah, sure. Let me just put the problem number 11 in the board so that all of you can see it. And you already have access, right, to the.
Yes, yeah.
So I am in the sixth board, Aryan, and I have put the problem here on the board. So here we go.
Yes, sir. So, this problem actually, when I first saw it, the first thought I had was maybe I would leave it, but the second way to do it in a very long way is use principle of inclusion exclusion. That's the natural way which I was thinking about when I first saw it. But there are four couples, so that would go very long. But instead, in the exam, I found one very short solution using casework. So I'll show that now.
Okay.
So, sir, I assume that the couples are as follows: H1, W1, where H stands for husband, W stands for wife, H2, W2, H3, W3, and H4, W4. So these are the 8 seats. Just a minute. So this is the merry-go-round. So, sir, without loss of generality, because the seats are identical, I'm assuming the males are sitting here. The circle spots.
Okay.
You can rotate the circle spots to get another confirmation, but it says the seats are identical. So we would just be overcounting. So without loss of generality, I'm assuming the males are sitting in these spots, and the women are sitting in the other four spots which haven't been circled.
Okay.
So, sir, I took one case where so total the husbands can be arranged in that is 4 minus 1 factorial ways, because all seats are identical and circular permutation gives that for n people being arranged in a circle, you have n minus 1 factorial ways to permute them, because it's not a line, it's a circle, so you have to divide by n. So this gives 6 ways to arrange the husbands in these 4 places on the merry-go-round.
Okay.
So, sir, I take one case which is h1 is here, h2 is here. This is one arbitrary case out of the 6, and we'll see that ahead that it actually doesn't matter. So, sir, then what I did was, obviously h1 is here, and by the condition in the problem, w1 cannot sit here and w1 cannot sit here, because then w1 would be next to h1. So w1 has two choices: either it sits here or it sits here. So,
Okay.
sir, then I assume the first case is w1 is sitting here. So clearly, if W1 is sitting there, we know W4, which is the wife of H4, she cannot sit here and she cannot sit here, because that's what they can't occupy seats which are next to their husbands. And so the only two choices are this and this. But since W1 is already occupying that place, this forces W4 to be sitting here. Similarly, W3 cannot sit here or here. So it must sit here or here. But since W4 is already occupying this place, it must sit here. And the only remaining wife, which is W2, is forced to sit here. So what exactly happened was we just fixed W1 and all other wives were fixed automatically because
Right.
of the condition of the problem. So
Uh-huh.
all we needed to do was just fix one W1
Correct.
and all others just, so there are, the counting becomes simpler. So uh, the second case also, if we assume W1 to be here, this was case 1. So in case 2, which is exactly similar, you can assume W1 to be here in this spot, and the argument is the same. This again forces W2, W3, W4 to be in exactly one position. So there are 6 choices for the husbands and only 2 choices for the women, leading to the answer as 12. This is the final answer.
Very nice. Very nice. Okay. Okay, that's great. Let me go to Shubhodip once. Shubhodip, are you there with us? Shubhodip, are you there with us? Hello. Maybe he is unable to speak or something.
Yeah, am I audible?
You are, yeah, yeah,
Okay.
yeah. So, would you like to comment on any of the problems?
Maybe the third one.
The third problem? Okay, go ahead and go to the next board then. That would be great. If you want, I could go to the next board. Third problem. In the meantime, I'll just upload the problem first here so that students can see it. Third problem. Okay. All right. It's here. So there is a set script T of all triangles whose sides are distinct prime numbers and also in arithmetic progression. And delta is an element of of that particular set with the least perimeter. So if a degree is the largest angle of delta, and if L is its perimeter, determine the value of a by L. Okay.
Okay. So this may seems like a problem in geometry. Yeah, indeed it is a geometry problem. So, but we would like to think about this problem from a very different perspective. So it's been said that the tau is script t, or I'm calling it as tau maybe.
Okay.
The tau is the set of all triangles whose sides are distinct primes, which are also in arithmetic progression. Okay, so we can think of this set as a collection of all tuples a comma b comma c, and such that This A comma B comma C, all these are distinct primes. These are all distinct primes, and they are all in arithmetic progression. That means A plus D be the common difference. So I have B, and B plus D, we have my C, the third side. And also they are the side lengths of a triangle. So what can we say from the triangle inequality? So A and B are the smaller ones. So we just need to check that A plus B is less than, sorry, greater than C. So if this is done, if these three conditions are there, and obviously the sides of the triangles cannot be negative. So A, B, C greater than 3 is always there. So from there, what can we get? Some observations we should make that first of all, A plus B, that can be written as A plus 2D, where the D is the common difference, and which is greater than C. And C can be written as A plus, uh, sorry, I'm making a mistake. So 2A plus D. 2A plus D is greater than A plus 2D. So solving this inequality, at least we get that A is greater than D. So now we think of this problem as a tuple of maybe three numbers, three distinct primes, and such that A, B, C are in arithmetic progression, and the common difference is always less than the first term. Now we can think that we cannot start, and we have to check the triangle delta to be the least parameter, the perimeter. The perimeter should be least. So for that, we need to have the first term, that means the A, to be the lowest. So 1 cannot be there because 1 is not a prime number. Now my first choice should be 2. My first choice can be 2. First choice 2. Now, what is the problem with my choice as 2? Note that whatever my second prime will be, it will be an odd number. That means we have to add an odd number with 2 to get the second one. B is odd and A is 2. That means the D, the common difference should be an odd number. But if the common difference is an odd number, then B being an odd number itself, B plus D has to be an even number. So the even number cannot be a prime. So C cannot be a prime. So my first choice 2 is absurd. So this cannot be my choice as the first side. So what can be done? Now my second choice for the least side, the smallest side, can be 3. Now once 3, we can check that all other numbers, the B and C, all those numbers are prime numbers and greater than 3. That means those are all odd numbers. So my common difference have to be an even number. And from this condition, we have what? The common difference has to be less than 3. So, what is the possible case? Only the possible case for D is equal to 2. Now we check, what do we get? We get 3, and 3 plus 2, 5, and 5 plus 2, 7. So note that all those numbers in this 3 tuple are prime numbers, as well as like my common difference is less than the first term. So it tells us that the triangle inequality must hold, because we arrived at this conclusion using the triangle inequality fact. So the triangle inequality will hold. So we get the triangle. Our desired triangle is at least this 3, 5, and 7. So this is my 3, 5, and 7. Now, A degree is the largest angle of the triangle. That means what? It will be the opposite angle of the largest side. So we say this is my alpha. We can say. Again, a few minutes ago, Aritro said that there is a cosine rule and he explicitly wrote it down. So what is my cosine rule? Cosine rule is 7 square is equal to 3 square plus 5 square minus 2 into 3 into 5 into the opposite angle. So what is the opposite angle of 7? The side with length 7, that will be alpha. So we just solve it. We have 49 minus 9 minus 25 is equal to minus 30 cos alpha. And from there, we get cos alpha is equal to minus half, I suppose. Well, so if cos alpha is equal to minus half, and alpha should be from 0 to 180 degree for obvious reason, because it is an angle of a triangle. So alpha is negative, the cos of alpha is negative, and alpha is within 0 to 180 degrees. So we can have that alpha is equal to 120 degree. So far, so good. And finally, what do we have? The last condition that we have to calculate L. We have our triangle of which each and every sides are the primes and distinct primes, and those are in arithmetic progression. And this is the least we actually checked. So our L is 3 plus 5 plus 7, that is 15. So the quantity asked in the question, that is alpha by L, that should be 120 by 15, resulting us that H. And this is ends the problem.
That's great. Thank you, Shubhadeep. So, just to make sure we understand what we are doing here, we are trying to have some fun with these problems. And when I saw this problem for the first time, the first thing that struck me is the green tau theorem. So, I'll just post it in the comment section so that you can all check it out. The green tau theorem. It's basically saying that, one second, yeah. The green tau theorem is a statement in number theory which says that there are arbitrarily long sequences of natural numbers, all of which are prime numbers and in arithmetic progression. So here the question, of course, talks about three numbers, right? Three numbers which are prime numbers, distinct prime numbers, and in arithmetic progression. Maybe you can ask a question that are there 3,000 numbers, all of which are distinct prime numbers, and then it is in arithmetic progression? Are there 59 million numbers which are all distinct prime numbers and all of them are in arithmetic progression? So the answer is yes, and that is a celebrated result in number theory. It's called green tau theorem. You can check it in Google. It's very nice.
Actually, it is a very special case of Dirichlet's result. The Dirichlet's result says that in any AP, there exist infinitely number of primes.
Okay, that's another case actually. Yeah, that's true.
Yeah.
Okay, very nice. Let me go to Oritro, and thank you all for attending. Again, we will have another session maybe in a very short amount of time on the other part B. But for now, we stop out here. Thank you, Arjun and Aryan and Oritro, Shubhadeep, Jatin, everyone for joining. We could not reach even Jatin with his wonderful ideas. They are all in cheenta.com. You can go there and check them out. But I really thank everyone for joining. We are having some fun with mathematics, and check out more things in cheenta.com if you want. Thank you. Take care. Bye.